All right, then with that, welcome again to Mansur, and please take it away.
All right. Thanks so much, Sylvia, and good afternoon, everyone. It's a pleasure to um, share this topic and presentation with you all. This is an ongoing project, have been for quite some time. So feel free to stop me at any point, um, in this presentation if you have any question. So today, I will be talking about how do we more efficiently sample failure rate if our goal is to validate um, how likely is our agent or our autonomous systems designed to encounter any sort of failures and under some um, random trajectory or disturbance model that we have. And the idea is then how, given the failure rate that we estimate, we can decide whether we need to improve the design much further or it's good enough for certain application. So that's the idea. I'm a research engineer or research scientist here working with Michael Kokendorfer at Stanford Intelligent Systems Lab, but I'm also co-appointed at Stanford Mineral X. Weirdly enough, well, probably not so weird, but people in sustainability, geologists, they also care about failure rate of any decision-making model because their stake is pretty high and critical. And therefore, they are also interested in applying some of the methods that we will be discussing today. Okay, so a little bit about me. Did my postdoc here also at Stanford last year. I just continue my appointment because I love working in the domain. And Sylvia also has worked a bit with Michael. So really great group to work with. And the topic they're working with is pretty interesting. I did my PhD in mechanical engineering at Carnegie Mellon. I work in the Safe AI lab over there with Ding Zhao. We both founded the lab, so I was his first student. And SLP is also pretty new. Starting a new group is quite daunting, but we did it, still survive at this point. So we didn't do a terrible job. My research is about certifiable evaluation for safe intelligent autonomy, and I will talk more about that. But this topic is a continuation of Ding Zhao's previous research at Michigan. So you may have heard people at Michigan doing important sampling for autonomous vehicle. Our group started there, and then we branched out to Carnegie Mellon. And now Michigan still continues working with M-City, the testing and validation center for the autonomous driving. I did my master's in Michigan in industrial and operations engineering. That's when I first exposed to autonomous driving, self-driving, and safety aspect of this new and cool technology. I'm from Indonesia. That's where I did my undergrad. Okay, so probably this is quite redundant with this class topic. CPS is everywhere. Lots of autonomous systems are being deployed, especially those that directly has some physical interaction with the real world. Some people call it embodied AI also. Whatever you call it, these systems are out there. It's in our transportation systems. We use it also to explore new mines or to place explosives in the field so that humans don't have to do them. We also deploy them for aircraft collision avoidance systems, which was the work that many people in our lab pioneer a decade ago or so. And these systems interacting more intensively and collaboratively with human, right? So it's not only making recommendations, but in some sense, they already make and implement the decisions they have made and actuate that in the real world. And more importantly, though, the type of decisions they make is becoming more and more important, even safety critical in many aspects. When does the Waymo self-driving needs to stop, or when should these robots plant the explosive so that it doesn't break the fault structure in a geological region, and what sort of advisories should the aircraft collision avoidance systems use to pilot all of these, making huge and safety critical decisions. And at some point, hopefully, we train them well enough, right? And they're being deployed, so that's great. But once they are safe, it's becoming much harder for us to validate their performance, right? And arguably, probably that's why Waymo and many self-driving companies are now, even robotics companies are collecting millions and millions more samples out there, not only to train their agent, but also to try to make their safety case, how likely they fail in naturalistic setting, or what failure modes should they anticipate, or how should they handle when they deal with these failure cases. So at some point, their failure rate might be small. And here I denote the failure rate to be mu, whatever that means in our context. In self-driving, it just fails to stop at certain, I don't know, distance from the leading vehicle. If maybe your robot trip, or maybe your manipulator just loose grabs or something, whatever failure specifications you have, once the agent is performing reliable enough, this failure rate becomes smaller. And when that happens, in order to observe the first random failure, we need 1/mu samples, right? This is just standard from statistics. But of course, when we validate these agents, we don't only need one sample, right? We need more. So imagine if the failure rate is, I don't know, in the airplane industry, they say it's 1 to the 10 to the minus 9 or something. Autonomous vehicle, maybe 1.5 per million miles of driving. Does that mean we should drive millions of miles to encounter one? I mean, that's just unwieldy, right? So what they do, and what we often think about is, yeah, if our goal is just to observe random failure, and we use the same observation or the same disturbance model that we would expect to encounter in the real world with the way we validate these things. Oftentimes we call it Monte Carlo sampling for the failure rate. This sampling procedure will have a huge relative variance, right? So what I mean by relative variance is you can, for example, generate a lot of random variables or random trajectory of your agent, or random disturbance trajectory in whatever space you want to operate. And then you pass that into your agent and evaluate whether it's fail or it's not. Maybe it's fail, you output 1. If it's success, you output 0. And then you take the sample average, you get your failure rate average approximation, essentially, right? I call that mu s here. So mu s is just the sample approximation for the failure rate. But if we do it Monte Carlo way, then the variance of our estimate is, relative to the true failure rate, it will be much higher, right? Imagine, for example, as mu goes to 0, this ratio will always be quite huge, right? And you can imagine also the variance of the mu estimate is square, 1 to the 1 minus mu over mu, and then we divide that by mu again. So that's why it just goes infinitely fast to infinity. So this oftentimes they call it relative variance. Some people call it coefficient of variation, or some other metric, coefficient of variance, or whatever you name it. But this ratio that you may use in order to make a claim about your how certain you are with the estimated failure rate is becoming extremely huge as the agent becomes safer, as this failure rate goes towards 0, right? Um, and in that notion, then, therefore, safer agent or smaller mu requires us to collect larger sample size for validation purposes. I think right now they coin it curse of rarity due to a paper from Michigan that's published in Nature Communications. So it's there's a curse of dimensionality, you all know probably. There's also curse of rarity at this point, that as your agent becomes better, how do you validate? Um, well, and of course, all of you probably in this class care about the safety of the system. So you want this agent to be ultra safe when deployed. So maybe you want to achieve some airplane level safety, 10 to the minus 9. That's absolutely great. We need to aim for that. So people becoming more confident in these autonomous systems being deployed. And hopefully people developing it are also a bit more reliable on the way they evaluate their systems. But this is just an illustration. This is a simple illustrations from when I did my dissertation at Carnegie Mellon. I have a really simple traffic sign classifier, like detector, deployed in Carla, and it has pretty good accuracy over, normal scenario. But you can easily make this, shift the distribution of your validation. For example, you can add noise to it, and it's super easily, misclassify the object. We know this, we know that some of the deep learning models are, just pretty brittle and not robust. When we change the distribution, there are much more robust models these days, but this is just an example. But what happens here is I intentionally tweak the validation environment to be slightly more aggressive. So I see what failure may look like. In practice, if I just run this in Carla, this may never happen, right? So it's really rare, but that you can tweak towards a certain direction and observe some failure cases, although it may be happening really rarely. Similar here, we can not only focus on the computer vision algorithms that's employed in these decision-making systems, but you can also, for example, evaluate, for example, here, the adaptive cruise control, or how far the AV should follow a human leading vehicle, to maintain a certain safe zone. There's lots of complicated control theory, and I believe Sylvia will know more than that. But the idea here that if you just assume some random perturbation and you train the agent, the AV, to be robust enough, then it's until, for example, you hit a point where the failure rate is already 10 to -5, then evaluating them becomes quite unwieldy. In this example, I think I spent, if I were to run a Monte Carlo sample, it will take me months, and I will not be here today. I'm still running my Carla simulation and collecting my data. No, don't do it. This is just a theoretical calculations that we show. I skipped the details, but there is some of these details in the paper that I shared with you, the second one. If you consider a certain true failure rate of the agent, whatever the true failure rate means, and you have some notion of what accuracy you want to achieve, so what is the relative discrepancy that you can tolerate in terms of percentage or whatnot. So the smaller this relative discrepancy, you want higher precision or more accurate estimate. And as your agent becomes more reliable, the number of samples, which we show already in the log scale here in the Y direction, in the Z directions, just blows up exponentially fast, right? So there is no way. I give you an illustration here to run I don't know, like a few million samples in Carla. Even though you parallelize it, it only takes a few seconds to spin up. It can still take you 5 years. That's the duration of my PhD. I don't really want to spend all that time just to Carla collect samples. Obviously, no, right? So you can see here, as the agent becomes more reliable, it's just becoming extremely hard to validate, right? And of course, when I mean validate, there are different safety validation goals, and you should be able to infer this from the first paper, the review paper I showed you. There are 3 major safety validation goals. One is falsification type, where your goal is just to find a failure trajectory that violates specification, right? And if you can do that, then the agent is falsified, and therefore it's not 100% safe. In many cases, you can do a falsification to certain systems, right? I'm not talking about this type, but of course, this is a fine a goal. And in fact, later, as I will mention briefly, you can use falsification for the other type. The other type is most likely failure. So the idea that now you acknowledge that, yes, some failure are more likely than the other, given some disturbance model, and your goal is mainly just to find the most likely failure. And how do you deal with that? And you can keep iterate and improve your agent. That's fine. The third type is what we have been talking about so far. It's failure probability. How do we estimate the failure rate, or how do we infer the violation rate given certain specification under some disturbance model that we consider a real life disturbance model, right? So it's sort of a probability distribution. It's we treat the failure as a random occurrences in the real world with some underlying um, probability distribution. Of course, this probability distribution will change as the environment shifts or as your agent becomes better and better, right? So these two type is mostly called probabilistic evaluation by people in the validation field. And that's what we will focus on mostly in this talk. But more specifically, we'll focus on the third type. How do we make sure that the failure rate of the agent we can estimate them quite sufficiently accurate so that we can make a validation decision? Is it safe enough, or do we need to train a bit more? This is just some figures that we come up with a couple of years ago at CMU, when we said that falsification validation has lots of ways that you can deal with. Adversarial learning is obviously growing field back then. There are many more methods right now, but it started off with more formal methods and grid search and so on and so forth. Probabilistic evaluation, there are lots of theories. Some that we highlight here is there's something that's called large deviation theories from statistics, and that's where the main topic that I will discuss to you about is coming from. So if you're interested in learning more, read about large deviations theory and variance reduction techniques. Some of these have been covered in many of your courses so far. Feel free to read more into the survey if you're interested about the other types. If you're more interested in the falsification, read Anthony's paper. That gives you a good understanding of how we deal with some of these types of safety validation goals. How do we generate validation test cases then? Well, now there are lots of ways you can do this. There's a good survey also by our colleague at CMU, Wen Hao, who is now at NVIDIA. So the idea is when we do a validation, whatever methods we use, we still need to come up with some way to generate danger scenario, or how do we trip the agent to make some bad decisions and therefore invoke failures, right? In this case, we mostly focus on autonomous driving, and therefore we call it safety critical scenario generation, but you can think of it as a more aggressive or more likely to induce failure scenarios. How can we do that? We can use data-driven generation, direct sampling, or density estimation. There are lots of references that you can take a look at. Feel free to look at the paper. But you can use data-driven generation and try to use the data that you have in order to come up with a new sampling that might likely induce failure. You can also do some adversarial generation technique, and this is more emergent. It's much easier to do these days. If we deal with black box, or if we deal with high dimensional spaces, because some of the techniques that I will mention to you is also still quite limited to not so high dimensional. There's also knowledge-based scenario generation, which I mentioned to you previously. If you know the operating conditions, if you know the expected or unexpected behavior of the agent, then you can create rules, or you can guide your sampling procedure using this knowledge and try to induce failure. So there are a couple ways to generate validation test cases. That being said, though, some of these ignore how likely they happen in the real world, right? If our goal at the end of the day is to estimate the failure rate under the conditions in the real world, we can't just tweak the parameters to be extremely aggressive, because it may never happen in the real world, and we become a bit more conservative in our validation results. So there needs to be some sort of balance of how can we do scenario generations with considering how likely we can estimate the unbiased estimate of the failure rate under naturalistic conditions. Let me pause here if there are any questions so far that you have in mind. Happy to take it. Okay. If not, feel free to type it in the chat. I'll try to monitor it as well. If not, I will continue. So this is just, again, what we talk about is just a way to generate validation test cases, but it's not, it may give us a biased result, right? If our goal is to estimate the failure rate. Well, there is this tool called importance sampling. Um, maybe many of you have been familiar with it. If not, this is a rough idea. So the idea is you have some naturalistic operating conditions under which you might, envision your agent to be deployed with. So here is an example, like a really old example that we have been using since we were in Michigan. Self-driving example where maybe, people are just nice and you deploy your autonomous vehicle. Obviously not here in San Francisco. People are not that nice currently. But suppose, you train your model using that and you can come up with some good agent. You train that, you have a good estimate, great. But under these naturalistic operating conditions, because that's how you train your agent, you collected already, I don't know, like billions of miles and have been able to train your agent sufficiently well, then if you test your agent, you may need what we just mentioned. You may need to drive or even simulate million of miles in order to observe some fatalities, right? This is highly non-efficient. This is the Monte Carlo approach that I mentioned previously. On the contrary, what you can also do is using the safety critical scenario generator, pipeline, whichever you choose, you can create an aggressive operating conditions, right? So maybe you train in the US, but you deploy, I'm from Indonesia. Try deploy autonomous vehicle that you train in the US in Jakarta. There is no way it will behave as nice, right? So if you can create a more aggressive operating conditions, and under these more aggressive operating conditions, you may encounter, failure rate more, more often, right? In higher frequency. But of course, this is a biased result, right? They don't represent the real world. So what importance sampling says is, well, that is true, this is biased, but that's biased if you use the Monte Carlo estimate um, for the failure rate. Again, a Monte Carlo estimate may be just, you take the sample average of whether you encounter some failures. And here, assume X is just whatever randomness you invoke into your scenario that makes it different from one run to the other. And you have some, say, some failure set essentially. And when this random scenario hit the failure set, you call that a failure, and maybe that's the output of your simulator, and you can take the sample average. This is our Monte Carlo estimate, the sample average approximation. Well, yeah, as we mentioned, if you do the same thing, this is unbiased. I know I don't need to explain that in detail, but you can. It's an easy exercise. You can take the expectation of this and show that the expectation is converging to the true probability, right? Um, it's straightforward. Now, what we say, well, yeah, you can make the aggressive, the environment more aggressive, but don't use simple Monte Carlo, but use importance sampling estimate. What is importance sampling estimate? It's the same thing, but you sample the scenario using the more aggressive environment. And then you take the likelihood ratio. So there are two likelihood here. The one in the top, the numerator, is the likelihood of scenario X under the naturalistic condition, right? And the one on top is under the more aggressive conditions. So this is what we call likelihood ratio, or some people call it importance sampling ratio or importance ratio. And using these new estimates, so it's still the same thing, but you generate the sample using more aggressive distributions, but then you multiply your estimate with this likelihood term, and all of a sudden we can see from the theory of the importance sampling is once you do that, again, this is just our importance sampling estimate, our binaries times likelihood ratio, where the likelihood ratio is the importance sampling ratio. We can expand the term, take the definition of expectation, take the linearity of the expectation, cancel out this term from the aggressive distributions, and you come back with your original unbiased estimate, right? So the key thing here is it cancels out. Does anyone know what is the requirement though for this to be holding in all cases? Is it to say because you take a ratio, then you need to make sure that ratio is defined, right? So in that case, you have to make, well, there are a couple of ways to do that. One way is to make sure that the support of your aggressive distribution is wider than the support of the naturalistic distribution to make sure that it's defined everywhere. You cannot just say, oh, okay, I'll make it more aggressive, but condition only on the dangerous distributions, ignoring all the normal cases. No, no, no. This ratio will be blow up, right? This will not define under that cases. So there are some conditions under which this can hold, but it's quite modest, I will say. So for example, if you use just, I don't know, multivariate Gaussian in both cases, you just shift the mean, this is still valid everywhere, right? Um, okay. So important sampling is theoretically unbiased, so meaning that the expectation of your estimator will converge to the true failure rate. That is great. And another thing, what we want is actually that our important sampling estimate has lesser variance, right? You want to make sure that your variance is smaller so that you don't need to keep that, I don't know, like yeah, crazily astronomical sample size in order to make your safety claim. I will skip many details here, but you can reduce the variance of your important sampling estimator using this formula. Just make sure that your more aggressive distribution is a conditional distribution of your naturalistic distribution conditional on where the failure case happened, right? But of course, we still need to make sure that it's defined everywhere. That's the only requirement. I'll show you how to achieve this more intuitively in a second. But algorithmically, you can use algorithm called cross entropy. And the idea is then you can parameterize your optimal distribution, your aggressive distributions with some parameters, and then you update these parameters over time. There is some way to do this. Cross entropy for rare event estimation is pretty well-known algorithm. Don't confuse this with cross entropy for optimizing, some functions. It's somewhat related, but it has a different flavor. But just look at cross entropy for rare event estimation, and you should be able to find some really good chunk of algorithm. This is pretty well known, so we can find a good proxy to what would be closer enough to the true optimal distributions using this iterative method. Okay. What does that mean though in practice? This is what I want to highlight more, and maybe you can also share your intuitions later on. What important sampling does is, so for example, you can come up with some naturalistic distribution. This is just an illustration in a 2D illustration where most of the scenario are saved, within your, I don't know, 3 sigma in each direction. So suppose you have a Gaussian center at 5,5 and your failure set is way over there, right? So you can see if you generate samples, I don't care, like maybe 1,000,000, you encounter only one sample hitting this failure set, right? So what important sampling says is basically just skew the distribution toward the failure regions. So what in practice, it just means that find your failure set, find the boundary of the failure set because it will have the highest likelihood, right, corresponding to the naturalist distribution, and shift your new mean toward that, and that gives you a good important sampling proposal.
Why just the boundary?
Why does the boundary? That's a good question, because if you see throughout this region, and this is our original distribution, if we want to find the failure set that has the higher likelihood under the naturalistic distribution, it will be the one closest to the original mean, right? And that's why it's on the boundary by definition. Yeah.
Could I ask a question?
Yes, please.
On the far right graph, I would expect to
Yep.
say Gaussian wings extending further into the failure set. Why does it look like that?
Yeah. So this is just the likelihood ratio already. So it is just that, ratio between the density of the naturalistic distribution over the proposal distribution, as we call it, multiplied by whether it is in the failure set or not.
Oh, okay.
Yeah.
Thank you. Thank you.
Yeah. So it's not a pure distribution per se. It's just the likelihood ratio value that we try to show here. And that's what you need in order to compute your importance sampling estimate, right? Everywhere else where it is safe, it will have zero because you multiply, there is that term, whether you are in the failure set or not. So as long as that one, and your likelihood is well defined, and most of the time it will be less than one, you take the average because it's less than one, then the variance will also less than one, and therefore you achieve this desired variance reduction. Maybe a bit too vague over there, but that's the idea. Other questions? Okay. If not, yeah, this is a really simple example, right? But I hope it illustrates the idea of importance sampling. So, you have a failure set, it's far away under natural distribution, just shift your distributions toward that. But don't be too aggressively though, because if you push it too far, right, then this ratio can be greater than one, right? If it's greater than one, then your variance will be not reduced, but even blow up. So that's why we want what we call optimal importance sampling distributions is exactly that. You want to shift it toward the region of the failure set where the likelihood is maximum under the original distributions, so that you have this effect of reducing the variance. That's the main intuition I want you to depart. So if you forget everything else, just think about that when people are talking about importance sampling. I hope that helps. Okay. If it's still not quite, feel free to reach out later. But that's the intuition behind importance sampling. And this is also true in high dimensional examples. A natural question though, well, this is easy because we only have one failure set. How often do we have that in CPS applications? I barely see any. Well, the good thing is this application is scalable to however many failure sets. If you have single failure set shifted there, you're fine. If you have multiple failure set, just make sure you can use Gaussian mixture model and shift your density toward each end. And you can still have the same effect of likelihood ratio being less than one everywhere in the failure region. You can have an infinitely many failure set, theoretically infinite, but then you can just create your mixture models centered around that, and you can cover all the failure modes, essentially. I skipped the detail here, but if you read the second paper I showed you, the reason why this is true is at the boundary, maybe this is a bit too detailed, but at the boundary, once you shift a Gaussian component of your mixture model toward one failure set, you can create a hyperplane essentially. And that hyperplane already covers that far side of the failure region. And therefore you cover this one, you need another one to cover this, and you keep doing that over and over again, right? And therefore this is also valid for infinitely many failure sets as long as you can cover the failure set that you can have. And why this is important? Because if you ignore, for example, one failure set, let's say you don't have this mixture, right? You only shift your distributions toward this failure set. Well, at some point, really rarely, but you can still sample that failure region, right? And that failure region will have a density under the original distributions larger than the shifted distributions, and therefore you have, again, a likelihood ratio that blows up, and your importance sampling variance also blows up. That's why you need to cover all the failure modes. Okay, so the key idea of importance sampling theoretically though, is you just need to control this likelihood ratio, making sure it's well behaved, making sure hopefully it's always less than one, but if you can't guarantee it's less than one, at least it doesn't blow up as quick. That's the only, that's how you can benefit the variance reduction effect from importance sampling. Okay, so you can have complex failure region, as long as you can cover them, you're still good. How do we find then all the failure boundaries? I need you to cover all the failure regions, right? The easiest thing is, if you do this research 5 years ago, or almost 10 years ago now, is just to learn the failure boundary using some deep learning model, right? So you can have, if you are able to collect some data sets, and if you can query some crash database in self-driving, they publish the traffic, the crash database, so you can utilize that. And therefore, you can collect the data, mark it with safe or failure, then train your neural net, right? And then from the neural nets, you can solve an optimization model to find the most likely failure, which lies on the boundary. There is a mixed integer programming that is well known in the OR field. There is a mixed integer formulation for feed forward neural net with ReLU activation, so you can directly convert your neural net predictions and find the failure modes, and that's what we do exactly in this case. You can use non-ReLU, but your boundary will be much more complex, and it will not be hyperplane. It's a bit more trickier to solve for the failure boundary, but you can still do that. But the idea is you can train a neural net and use your neural net to then find the boundary of the failure cases. You can use, again, adversarial attack. You can use falsification method that we just talked about early on in order to find that failure region. There's a boundary attack in full box, a package for running adversarial learning method. And there are much more, ways to do that right now. But the idea is train a neural net, find an approximate boundary for your failure regions, and then do the same thing. Shape your distributions toward that, then you're good to go. And that's what we call deep inference sampling back then. Okay, and how does it work? Well, we evaluate it under a few driving scenario benchmark. There is a benchmark called Safe Bench, which allows you to run more easily Carla scenarios, which is an autonomous driving simulator, to collect samples and evaluate the performance. We use that, and what we show you here is how it performs. So the green here is the deep inference sampling approach. We call it DeepIS. And we compare that with the true failure rate, which we compute like using tens of millions of samples in this case. And it shows that it's converging quite well, right? And you can also see the relative error, which is the metric that they show you, the variance over the true value. We are doing pretty well. We achieve 4x less samples, a much faster evaluation result. So the idea is just use, train your model, and then collect a sample, and then train a deep learning model, find the failure rate, and then, shape your distributions towards those failure modes, and then run your inference sampling procedure. That's what we do over here. You can also see, of course, some algorithms are underestimating the true failure rate, some over approximate. The neat thing, I think, is if you can go away with the over approximation, that is a good case because you can terminate much early. So maybe in your applications, for example, when someone asks you how safe is this algorithm, and the true failure rate is maybe 10 to the minus 9, but maybe if they are good enough with 10 to the minus 5, right? And you can come up with an upper bound of the true failure rate, but it's still less than 10 to the minus 5, then you can guarantee the true failure rate is below that, and then you're done. Your agent is already safe, right? Given that threshold. So if you can come up with an upper bound, and that upper bound is good enough, use that, because most of the time you can terminate much early. Okay, any questions so far? Nope. Okay. Feel free to raise your hand or type it in the chat, or just unmute yourself if you have any, but this is like a preliminary result. The highlight here, okay, it looks good in paper, but in practice, we may not be able to learn the failure rate. And I don't tell you whether I can cover, I don't even know whether I cover all the failure rate. I'm just lucky enough, it never happened in my validation samples. I don't know, I might also just underestimate the true failure rate. So it looks good, but we don't know if we have an accurate enough. And if we are inaccurate, the question is then, for validation task, we don't want to underestimate the failure rate, right? It's really safe if we say the agent is 100% safe. which is a lot of people are claiming these days that their agent is 100% safe, never encounter any accident. Okay, fine. Um, right? We don't want to underestimate the failure rate. And the second thing is what I mentioned in the last slide. Can we terminate early if we can account for overestimation? Because it seems like, if that's already good enough, we can terminate early. And these two questions inspire the work that you read, the main paper I shared with you, which is deep red, right? Because we don't know our neural net approximation is accurate. Too bad. Can we just at least get an outer approximation, right? And if we know that if we outer approximate the true failure set, then at least we have an upper bound for the failure rate, right? So that's the only motivation here. So because it's really hard if you look at the equation again of the likelihood ratio, the bad thing happens for important sampling estimator if we have a false negative, meaning that we say things are safe, but it's actually not. That's really bad. We can go away with false positive because it just means we over approximate the failure region. That's still fine. Because the true one will always be flagged as one, right? And therefore we never have this blowing up likelihood ratio. That's the motivation from sampling point of view. Practically speaking, we don't want to underestimate the failure rate. And therefore, can we just use an outer approximation? Again, this is my first encounter with training my own deep learning model, so please apologize if this is really rudimentary for many of you, especially these days. So what I think, okay, the easiest way to find an outer approximation for a neural net is just to increase the decision threshold, right? If you train a balanced network, then most likely you can get some decision threshold. If your decision boundary, if you're just predicting whether it's 0 and 1, and you take the difference of the two scores and then call that as your decision threshold. And you can increase one side to the other to get either an outer approximation or inner approximation. What we did here, because we want an outer approximation, we just keep increasing the decision threshold, or in this case, decreasing it, and it will give us, more and more conservative outer approximation. And we have a way to make sure that, what is the the PAC guarantee that we can get if we tune it this way, given a certain coverage assumption, all of that. I mean, we have that in the paper. I'll not bore you down with that, but there is a way, that you can systematically keep tuning your decision threshold toward what end to hopefully guarantee your outer approximation and get away with that, right? So that's exactly what we do here. So it's just deep inference sampling with threshold tuning to get an outer approximation. Of course, from the classical operations research folks, which we have collaborated back then, is they said, well, why don't you just take orthogonally monotone whole, which is also giving you which is that rough boundary that give you an outer approximation. It's rough, but it's an outer approximation given the data that you have. Fine, you can also use that. And in fact, we call it lazy learner in the paper. If you read the paper, and we use that as one of the benchmark with our threshold tuning parameters. Of course, now people learn a lot of outer approximation neural net, and there are convex approximations that you can also read out, in these directions. But essentially, whatever gives you an outer approximation for your target, you can use that for deep rate. That's the motivation anyway. And with that, you can see that, now our goal shifted slightly. We don't care about accurate estimation. We care about tight upper bound, right? And that's what we show in the paper. We scale down the rarity parameters. You don't need to know what rarity parameter means. It's just as you increase this rarity parameter, your failure rate, the true failure rate drops down significantly. And what we try to test here is our upper bound hold steadily. Hopefully it doesn't grow to conservatively, but now we deal with 10 to the minus 5. It's still quite decent, I'll say, right? If you have an outer approximations around 10 to the minus 22 or something like that. What we show here is we can deal with curse of rarity. That's our motivation. If our true target is much smaller, deep prey still give us some upper bound, and you can still terminate quite early, shown by some statistics in the paper. In some cases, we terminate 2x, 3x, or even 10x when it's really rare. Maybe it's rarely in the case, but at least we have that. And we benchmark a couple other models. Cross entropy is one, lazy learner is one, and deep prey is one. There are lots of benchmarks that you can also think of. So that's the idea of the second paper that I try to show you here. Okay, so that's great. We have a theoretical guarantee. I don't show you the theoretical guarantee in this presentation, but there are a couple in the paper. There is a guarantee for our conservativeness. There's also a guarantee for our efficiency as we go to more extreme cases. So if you're interested, happy to chat more about that. But from practical point of view, this is great. It gives us an upper bound. We can terminate much earlier. The only questions is then, because I only use threshold tuning, so it scales really bad in higher dimension. You can see if I just tune one directions, and the decision boundary, it can get extremely loose as we scale up in the higher dimensional space. And also, in some cases, it's not easy to guarantee an over approximation. In fact, we have an example of self-driving vehicles. It seems like it gives us an over approximation for a failure set, but in practice, you don't really know, right?
Can you remind me of the cases where you can guarantee it?
When you can guarantee, yes. So there are cases, for example, where your data only cover one side of the half, of the subspace, and there are some tiny, failures that's on the other side, but you never get to learn that from your data, and therefore, no matter how robust you try to make this, you never cover that other side, right? There are of course heuristic, like if it's already too small, then maybe you assume that's failure. I mean, there are lots of heuristics, but it's it depends on on the applications you have in mind. I think, in fact, in some of the more recent work that we are exploring right now for manipulator, with complex contact point, it's not so, it's not that when you grasp harder, you will always hold, and you grasp looser, the object will fall. Sometimes you grasp harder and it just slip and then it falls, right? And therefore, the failure region is not only on one direction, and it's just hard to get an upper approximation. All right, other questions?
So I have a question.
Yes.
Excuse me. So if you could go back a couple of slides, please.
Sure.
Yeah, right up there. So those two dominating points that I see,
yep,
those are the points where you're going to shift your distribution to
yes,
to do the importance sampling. Yeah?
Exactly, yes.
And could you talk a little bit about those hyperplanes, what they're doing there?
Yeah. Thanks so much for bringing that up. That's so there's a rigorous definition of dominating point. I call it just the most likely failure modes, because as a hand wave. But there is also a rigorous definition in the paper. So a dominating point is called a dominating point if, for example, well, I think we have a definition for dominating set, which is the set of all dominating points. A dominating point is defined by it's a point in the target region, in the failure region, right? And when you take a hyperplane that you build based on the Jacobian of your original distributions, right? So if you see, it should be tangential to that region, roughly speaking, right? That's the hyperplane. And the idea here is we use this hyperplane to determine how many dominating points we need in order to cover this rare event set. In this case, if it's only single failure region, yeah, one dominating point is enough because all part of the rare event will be on that region. In this case, this dominating point covers only all these dominating points because essentially the likelihood of all points on this side of the failure region is smaller already than that, right? But you still need to cover another part of the dominating point, of this region. Is that clear?
Yep, that makes sense. So it's like a little bit like separating hyperplanes.
Separating hyperplanes, yeah, exactly.
Got it.
Thanks so much for
Thank
that
you.
question.
Thank you.
Yep. Okay. So let me try to finish up. Yeah, so this is the limitation. This is great. It can't handle high dimensional space. But I would imagine now, again, the deep learning models, there are better ways to get an over approximation, right? It's really private. I think there are just a few papers I reviewed last year, and some of them addresses this point exactly. So I'm like, oh, this is pretty cool. We can update deep rate using this model. So the key takeaways is these methods that I've showed you, it's great to use. For example, if you care only on validation tasks, right? What that means is if your goal is to say, oh, how, is to answer how safe is this agent compared to certain standard, right? Like many people expect, like, can we get a self-driving vehicle that is safer than human? Well, if you have a good benchmark of the human, and if you can construct an upper bound that is tight enough that can answer that questions, then many of the models that I showed you is pretty good, right? But of course, many of them are in high dimensional space, so you still need to check whether the upper bound you get is meaningful and sufficient, to compare to the standard that you're trying to comparing it with. It's not, deep array essentially, and even deep inference sampling, because we don't know the accurate failure region. In the case then yeah, it's still good, but it may not be useful if you really need the exact failure rate estimate. That's why I frame this as a validation task, right? It's not an estimation task per se, but it's a probability estimation for validation task. So it's still pretty good in that notion. But if you want the exact failure rate, then maybe it's really hard to say, especially in the black box cases. Scaling up to high dimensional problems is still a major challenge, which is a bottleneck right now. All the applications are in high dimensional problems, but you can see that this is quite modular. You can probably replace one components and then try to see if it works, do lots of modifications with that and see if that, in fact, that in practice, that in many cases, that seems to be quite sufficient already to handle some computer vision, because we know, for example, in computer visions, some directions give you outer approximations and the other are not, in some loose speaking terminology. If you are interested in learning more, you can read this more theoretical book from Bucklew, Introduction to Rare Event Simulation. It's again from statistics and OR. It can be extremely theoretical, but it gives a good example, and it defines even what we mean by dominating point, what we mean by being dominant, and so on and so forth, which I don't really explain in detail. Exactly, the hyperplane notion is from this, so feel free to check that out if that caught your interest. What I will go through is just a couple more recent work that builds upon this, and I'm happy to take any questions. So some more recent work. Okay, I'm working more on inference sampling, and as many people in the lab. Now, can we make it a bit more, I don't know, like, up to date with the current deep learning phase? Okay, so people do normalizing. Okay, flow model, is it applicable? Yes, you can combine normalizing flow with inference sampling. What is the benefit? Sadly, this is, normalizing flow cannot help you with dimensionality reduction because it still needs to be, back and forth. But what it gives you is you can have a really complex failure region in the input space that might be hard to model, but maybe it's much nicer in some latent space, right? And in that case, using normalizing flow is pretty useful. This is a paper that we submit. It's still in archive, but I think it will be in AAAI, in the next coming months. But we provide a couple examples, more like autonomous systems in an holonomic robot. There are F-16 simulator, lots of examples if you're interested to that. So check out the paper if you want, but this is the idea. So you can have a more complex failure region in the target space, but maybe in a complex distribution conditional to those failure set. But in the Latin space, maybe it's much nicer, right? And therefore, you can apply importance sampling more easily in the Latin space using your normalizing flow mapping and then convert it back. And we can say, it seems like, although we don't prove it theoretically, it seems like the true, the both value converges to the same value. We are still working out some of the proofs, whether, why the mapping conserves all the density mass, especially in detail, but there are still a couple challenges over there you try to encounter. But practically speaking, it doesn't look so much worse. The other work, which is the bonus paper that I share with you, is can we, use the failure modes that we obtain during validation and improve the agent and do this iteratively? So can we close the loop essentially, right? And that's exactly what we do here in this paper, which is published in Robotics and Automation Letters. So we use importance sampling mostly on validation early on, but then now can we use that, importance sampling proposal to generate more samples and to retrain our agent and doing it over and over again? Because if you know the failure modes, that's pretty useful information, right? To retrain your agent. Why not use that information? In fact, that's what we do. We show this in a self-driving vehicles under roundabout and intersection, dealing with high density traffic setting. So you can see here, for example, we start up with cross entropy with a single mode, and then we add a new mode that we find in the next iteration that gives us these 2 modal distributions, and then 3 modal, and so on and so forth. So we keep adding samples, update our evaluation, and doing it over and over again. And it seems like it works pretty well. The success rate for the agent, which we define as being able to navigate this intersection, is great. It's improving, collision rate declining, and timeout rates declining up to a certain point, right? At some point, no matter what you do, there are still cases where you just cannot train the agent. We still don't know why. Maybe it's just the control limit that we pose in the simulator. Maybe it's something else. But a few examples we see, if there are sudden acceleration, like adversarial behavior, no way we can deal with that. If you have an overcrowded scene, you will always have timeout rates. There's no way to deal with that, right? So we can use also the generated samples to retrain our agent. Some more recent work, can we deal with Gen AI? Well, yeah, let's start with diffusion model. So we have a diffusion model plus importance sampling, which we call diffs. We're not that creative in name currently, but we have diffs paper. So can we use diffusion model as a proposal distributions? And we have this paper up in the archive. It's still under review at a conference, but you can take a look at how can we integrate diffusion model in coming up with a more reasonable and versatile failure set estimation and correspondingly importance sampling proposal. That's all I want to discuss. I'm thankful for many collaborators that I have here at Stanford, Michael, Jeff, at CMU, Ding, at Columbia, Henry, UIUC, Bo Lee. Recently I worked with Jachan and David, and many folks in the CISO. So thank you very much. I'm happy to take any questions.
Thank you so much. And thank you also for the analysis after each of the parts of the talk on kind of where this works well and where this doesn't. So that already handles that question. You also gave us lots of resources to point towards learning more. So I guess the last of the questions that I asked you ahead of time was kind of a little more abstract in terms of what are the major future research challenges for this method and safety for autonomous systems in general that you foresee.
Yeah, so That's a bit nuanced to answer at this point, I feel like. My main challenge, though, is whenever a sponsor or even in practice in the industry, when I talk about safety validation, they always think like it's not part of the training. You do it post-training, and therefore it slows down progress. I think it happens everywhere, right? That's really sad. So whenever I talk about, well, do we have a really cool validation technique? They said, yeah, but we are not even at 99% safe yet, for example, or we want to make this much higher safe before we even care about safety. So I think one of the major challenge is, and I think it's also partly maybe it's we need to think together how to reframe safety validation as part of an integrated training process, right? We need to bring validation closer to training process and not doing it post hoc, because I feel like industry just don't want to do that, you know. That's number one. And because industry doesn't want to do that, and therefore it's really hard to convince people this is an important issue. Although people now in LLM, well, they're branching also, right? Some people want to really aggressively deploy their system. Some people are also quite, not sure how to validate the safety of their agent. So that's number one. I think the way we view validation as a post hoc training is by itself is non, is just not attractive for many people, right?
Is this
That's
part of
number one.
what has inspired things like the RAL work to try
I
to
think so.
show that
Yeah.
this is
Yeah, exactly. Yeah, that's to the point. We try to make sure, oh, with this, you can improve your agent and go and
Mhm.
so on and so forth, right? So that's part of our motivation. I think number two is right now, many of these, um, work that we show, um, I don't talk this much, but in the deep ray paper, one of the reason why we use outer approximation is because if you see in the deep IS, we have a really nice result, and I can stop at that already. If I don't know more, I can say, oh, I have really cool applications, for my algorithms. I did it, but looking at closely, it can still underestimate the true failure rate, right? So it's really hard to see like when this algorithm is actually giving you a good guarantee and when it does not. And people can say, and I think that's also what happens in practice right now. You can easily claim your agent is 100% safe, and only to find out later that there is some failure cases that you have not covered just yet, right? Um, so in this direction, it's hard to, especially when we talk about data driven and as the complexity of autonomous systems to deploy in the real world gets more complex, it's really hard to say whether we truly have a theoretical guarantee. And even the type of guarantee we can prove is really theoretical. I prove the theoretical guarantee for the conservativeness of I don't say it's correct, right? I can say, oh, with this probability, I'm this percent approve, up. Or I can also say with this confidence, I can say that, I can, the sample size that is needed in order to evaluate this level of failure rate is not exponentially growing. It's only polynomial. Well, in some cases, polynomial is still quite large, right? So I think there is still a mismatch, and I don't know how to make it a bit more practical. And it's really hard to do this one or the other. To link it back to the deep prey paper is the good thing about deep prey is you can just use deep IS and then just convert that to a deep prey, right? By tuning something small, but then you have it all the theoretical guarantee, but you lose accuracy, of course, right? And I think trading off accuracy and the goal of the task is something that we need to talk more. But I think this is also something that people don't talk often. I feel like if we are clear with our requirement, what we really expect for these robots to do, then we can say, oh yeah, 10 to the minus 5 is enough. And therefore, if you give it 10 to the minus 6, maybe that's fine. But people always say, okay, that's good enough. But what about, can you make it much safer than human? Can you replace human? And the expectation just keeps growing. And it's just really hard to chase that goal. I know it's really, loaded answer, but I hope it points to some of the directions and the challenges in the field.
I knew what I was getting myself into with that question. So yes, thank you. Okay, other questions?
Yes.
I have another question, Professor, if you don't mind.
Yes, please.
Maybe you answered this already, and I must have missed it, but could you tell us or tell me how you learn the failure set, please, using your neural
Yeah,
net? What's the
yeah,
data, and how do you go from just the data of, say, crash reports or whatever, and how do you go from that to having a set representation of your
yeah.
failures?
Great. Yeah, that's a really good question. So let me go back to that example. So let's say here, right? So you have
Yeah.
crash database that if you save or not save example, well, from the crash database, you get mostly the red samples, right?
Mhm.
But from there, you can, you basically train your neural net of choice, whatever you have. And from that neural net, you can tune essential decision boundary, right? Whatever you set, let's say you fix it at certain point. Now, with that, uh, um, with that fixed, then what we do in this paper is we use mixed integer programming to try to find the hyperplane.
Oh, I see. I see.
Yes. And that's why if you read the paper, we have like mixed integer programming for feed forward neural net with ReLU activation, because that's the best we can get by then. And that's also why you see in this example, I only use ReLU activation, and therefore I get this, piecewise decision boundary.
Right.
Yeah.
I see. I see.
But I think the idea, if you have a way to come up with that set representation, you can already use that, right? Again, this work is, I think that's also the reason why we publish it in AI Stat, because it's rather theoretical and give us a framework to how to think about the problem without focusing on the specific technologies that we deploy to get each specific component. We're just excited, oh, deep learning can be used. And we know people are, deep learning field is rising really fast. Hopefully people figure it out how to scale this up that's what we rely on. Okay.
So am I right in saying that you're trying to classify points, basically? You're trying to
Exactly.
say,
Yep.
does this belong to the failure set or not? And then
Yep.
you're trying to get a simple decision boundary so
Yep.
that you can apply those dominating points, hyperplanes
Yep.
to get your.
Exactly. Yep. Yeah.
Right. Thank you.
We tried much simpler approach. You still need to train some model. It can be crazily complex, and you just attack it using adversarial attack and find the point in the boundary, maybe using fast gradient sign method. You can still get a decent result, but we just cannot prove its correctness because there's no guarantee, at least to the one that I know of, that if you apply adversarial method, you cover all the failure set. If any of you know how to prove that, talk to me. Love to collaborate, because then you can relax many of this and say, just use, adversarial attack and you're fine. That's why we say you can use falsification method to give you some of, the failure set and then use that as a dominating point, And as you get more and more, just find the one with maximum likelihood, shape your distributions towards that, and you have your important sampling distribution. Good questions. Other questions?
All right, I guess that's it. Thank you so
Okay.
much again for taking the time, Mansur.
Yeah,
Really
thank you so much.
appreciate
Please
this.
stay in touch if you're interested in safety validation work. Happy to connect with you. And thanks so much again, Sylvia, for reaching out to us.
Of course. Thanks. Bye-bye, everyone.
All right, bye everyone.